So it's now recording and we can now begin. So let's start off with right here to conversion. So mole conversions. So from mass to moles, etc. Right? So let's start off with the first thing we have here, which is 1.73 moles of sodium hydroxide to grams of sodium hydroxide. So who can tell me how can we convert my moles of sodium hydroxide to grams of sodium hydroxide?
Multiply moles of sodium hydroxide by the molar mass.
And let's do that. So if we set up our dimensional analysis where we have 1.73 moles of sodium hydroxide, and like you said, we multiply by the molar mass. And what is the molar mass of sodium hydroxide? Who can tell me? Anyone can.
What was the question again?
40.
It's like 39, 30 something.
I got 40.
40, 39 point, etc., etc. Yeah, around the same stuff, right?
I rounded.
We'll put 40 grams of sodium hydroxide. And remember, since molar mass is grams per mole, saying that for every 40 grams of sodium hydroxide, we have 1 mole of sodium hydroxide. So our moles of sodium hydroxide, they cancel out. So here, real quick, Sophia, can you check? Am I actually recording?
Yeah, it says recording.
Okay, perfect, because it doesn't say on my screen. I just want to make sure. All right, perfect. So now that we've canceled out moles of sodium hydroxide and we're left with grams of sodium hydroxide, what does that give me?
You multiply 40 times 1.73, which give you 69.2
Exactly.
grams.
69.2 exactly grams of sodium hydroxide. So let me quickly clear this up. That's perfectly correct. And let's write that here. We get 69.2 grams of sodium hydroxide.
I had a question.
Go ahead.
So in the test, when we're doing molar mass, would it be better to add it with the exact decimals or to round?
In terms of, just converting from moles to grams and vice versa, you can safely round. For me, I like to use decimals. So I personally like to round to either the first or second decimal place, depending on the element. So for example, oxygen has like 15.999. Something like this can be safely rounded up to say 16. But something like hydrogen, which is like 1.008, I like to round this up to 1.01 using some decimals there for some accuracy.
Oh, okay.
And then also keep in mind it's multiple choice. So whether or not you decide to round, you should be able to get a close enough answer that you can pick from the multiple choice.
Okay. Thank you.
You're welcome. So moving on to the next one where I have 0.274 grams of ammonia. How can what do I need to do to convert my grams into moles of ammonia?
Divide by the molar mass.
I will divide by the molar mass. And what is the molar mass of ammonia?
17.
Can you speak up a little bit, sorry?
17.
Roughly around 17, yeah. So 17 grams of ammonia. And remember, it's a ratio where for every 17 grams of ammonia, we have 1 mole of ammonia. So if our grams cancel out, we'll be left with moles. And who can tell me what number does that leave us with?
Um, 0.0161 moles of ammonia. Shouldn't it be NH3 instead of NH4?
Oh, NH3, yes, my bad. I actually put NH4. So it is NH3, not NH4. So thank you for catching that. So it'd be 0.0161 moles of ammonia, not ammonium. NH3, there we go. Good job. So on to the next one, which is copper, where we have 76.2 grams of copper to moles of copper. So what do I need to do to convert that? given what we've just been doing so far?
Divide by the molar mass again.
And what is the molar mass of copper?
63.55.
63.55 grams of Cu. And remember that for every, grams of an element or compound, there's 1 mole of that element or compound. So our grams, they cancel out. And what value or number am I given after calculating this?
.20 moles of copper.
And why are we being specific of 1.20?
Because of the 3 significant figures?
Exactly, perfect. Since the number we're given has 3 sig figs, our final answer must have 3 sig figs. So that's exactly correct. And on to the last one for number 1 here. I have 1 molecule of O2. How many grams is that? So what's the first step I need to take in order to go from a molecule towards a mass?
And the molar mass?
You're on the right track. That is a step, but not quite. Remember, this is not a mole. Where a mole is something else. This is a molecule, meaning we have only 1 O2 molecule. So this is an O2 molecule. There's a singular one of this. We're trying to see how much this 1 molecule weighs in grams.
Oh, it's 6.022 times 10 to the 23rd, right?
Exactly. And what number is that exactly? Do you remember the name?
Avogadro's number.
Exactly. Okay, so Samuel, the recording will be on the Pure Leading YouTube channel, if you can hear me still. And the link for that, your Pure Leader should be able to provide that. If not, let's see, can someone provide in the chat real quick while you continue? But it'll be uploaded there either later today or tomorrow morning. So for those of you that had to leave early, don't worry, this will be there. So moving on, like you said about Avogadro's number, what do we need to do with that number in order to work our way towards a mass?
Divide it.
We would divide it, right? So we have 6.022 times 10 to the power 23. In this case, molecules. So a molecule of O2. And remember, for every Avogadro's number, there's 1 mole of that substance. So 1 mole of O2. Our molecules, they cancel out. I'm just going to continue this down here because I ran out of space. So now that I'm left with a mole of O2, how can I go from moles of O2 to grams of O2?
You divide by moles.
I'll divide by moles. And if I need to divide by moles, what do I need to multiply by in order to get grams?
The molar mass.
And what is the molar mass of oxygen gas, specifically O2?
32.
Can you repeat that, sorry?
32.
Exactly, 32. So it'd be 32 grams of O2 over 1 mole of O2. So our moles of O2, they cancel out. And now that we have our desired unit and compound, all left to do is to multiply the top and divide by the bottom. So who can tell me what do we get when we do that?
So from this point, you just divide Avogadro's number by the molar mass?
Basically, since in the end, you're kind of multiplying 1 a lot.
Okay.
So
5.31 times 10 to the negative 23.
5.31 or 5.32, around that range is correct. Times 10 to the power of negative 20. What, can you repeat that number again? To the power of
23.
23, exactly. And this is grams of O2. Remember to specify your units. And with that, we're done with number 1. So
I have a question.
Go ahead.
I'm sorry, I joined a little bit late. Can you just briefly explain to me how to get moles to grams and then grams to moles?
So if you remember, if you look at the periodic table, the weight or the number underneath the element is its molar mass, meaning it has a mass of, for every gram of that element or compound, there's every 1 mole of it. And you can look at this like a ratio where, let's say, for example, oxygen, right? Or where oxygen has a molar mass that's rounded up to 16 grams per mole. Meaning for every 16 grams, there is 1 mole and vice versa. So if I have a mass, let's say number mass of O2, and I want to convert to moles, I need to divide by this grams to cancel it out and multiply by a unit of moles in order to keep my moles. So since this is a conversion ratio, I can place this in my dimensional analysis. Now, it doesn't matter what goes on the top or bottom, since they're both equal to each other. So how can I place my numbers in my table in order to cancel out my grams and be left with moles?
I would multiply.
You would multiply, but which of these two numbers goes on top or the bottom? Because remember, whenever you're in dimensional analysis, you're multiplying the top and dividing whatever number is at the top by the bottom.
Wouldn't it be 73 times 16?
73.
So like 16 on the bottom.
You would put your 16 grams at the bottom, because remember, whenever you divide by units, they cancel each other out. And whenever you multiply by a unit, it gets added on to your final answer. So like so, you would have your grams would be divided and you'd be left with moles. So grams would cancel out. And the same thing applies from moles to grams, right? So instead of having a set number of, say, grams, I have a set number of moles. And I look at my conversion ratio, which is the molar mass of O2 gas. So every 16 grams, there's 1 mole and vice versa. So I would put my mole at the bottom in order to cancel out moles and my grams at the top. So they would multiply across.
Got it. Okay. Thank you.
You're welcome. Are there any other questions?
Real quick, if you need extra help, page 87 in your workbook has a really good visual representation of how to do those calculations. Just make sure you also know how to set them up using the fence post method, but it's a good way to start thinking about how you're going to attack the problem.
Okay, cool. Thank you. Appreciate it.
Perfect. Thank you, Brooke. So going on to number 2, where it's asking us how many ammonia molecules are in 1 mole of ammonia. So
if it's just one, wouldn't it just straight up be Avogadro's number? Just 1 times the number?
Exactly, right? It would be, since you remember that for every 1 mole of a substance is Avogadro's number of that substance. So what is Avogadro's number?
6.022 times 10 to the power 23.
23, and then we put, since it's asking for molecules, it would be molecules of NH3. Exactly, perfect. Now, moving on to number 3 of what is the mass in grams of 1 mole of ammonia?
This is asking for the molar mass, right?
Molar mass. Since we're going from moles to gram, we have to multiply by the molar mass.
And what would be the molar mass of ammonia?
17.
It would be 17. You can safely round it up to 17, right? So it'd be 17 grams of ammonia. Because remember, for every 1 mole of ammonia, it's equivalent to 17 grams of ammonia. Perfect. Nice. Like easy stuff, right? But it's good to get into the habit of this, because trust me, this is chemistry for the rest of chemistry, really. And so for number 5 here, we have a compound of titanium and oxygen that is composed of, by mass, 60% titanium and 40% oxygen. And it's asking us to determine the empirical formula.
I think you skipped a number. Like the 17 grams is supposed to go in number 3.
Yes, I see now.
And then for number 4, it's asking for 1 molecule.
Thank you. Sorry about that. Yes, thank you for noticing that. So on to number 4 before we move on to percent composition. So what is the mass in grams of 1 molecule of NH3? So who has an idea of how we can solve this, given that we have 1 molecule of NH3?
You divide by 6.022 times 10 to the 23.
Exactly. So we divide by Avogadro's number. So for every Avogadro's number, there's 1 mole of the substance. So our molecules cancel out and we're left with moles. Now, how can I convert my moles to grams now?
Wouldn't it be a positive 23?
No, it's negative 23 because Avogadro's number is such a small number that it's so far off the decimal point that's too big to write. So we write it in scientific notation. Oh wait, is it? No. Am I
No,
wrong?
it's positive. 'cause it's
Yes.
a big number.
Oh my God. Yes. Oh my God. Sorry. Just a lot of things running through my mind. I'm sorry about that. Yes. Thank you for
I'm
catching.
just testing you. He's making sure you know what you're doing, which
No,
apparently you are. So kudos to you.
We all know that's wrong. It's been a long day for all of us.
Yeah, Avogadro number is not negative.
Yeah. Thank you for catching on that. I'm so sorry about that. So we have the correct Avogadro's number and we're left with moles. How can I convert from moles to grams of a substance?
Multiply by the molar.
Only by the molar mass.
Exactly. And since we have it from problem 3, we just plug it in as so. Since we'll multiply it for every 17 grams of ammonia, we have 1 mole of ammonia. So our moles cancel out, and now we're left with grams. So what number would I get for solving this? So multiplying across and dividing by the bottom.
(2.82 times 10 to the 23).
2.82 times 10 to the power of negative 23. Is it? I got that on my calculator for some. Yeah, because you're dividing by Avogadro's number, so then that exponent then become negative. Exactly. So perfect like that. So that grams of NH3. Perfect. So if you guys have any questions, just feel free to interrupt me if you want to say out loud or put in the chat. The peer leaders will be happy to help. And so now on to number 5, now that I haven't skipped it this time. So going back to a compound of titanium and oxygen composed of 60% titanium and 40% oxygen. And it's asking for the empirical formula. So who has an idea of how I can find my empirical formula from this?
First, you have to convert percentages to grams.
So if I take my 60% of titanium and 40% of oxygen and just straight convert to grams, nothing specific, no steps.
No.
Exactly. So because we assume, so for those of you that may not know or remember, since it's 100% of the sample added up, we assume that it's 100 grams. So we just straight convert our percentages just to grams. So we have 60 grams of titanium and 40 grams of oxygen. So now that I have that, what's the next step I can do here?
Divide by the molar mass.
So let's divide by the molar mass. And what is the molar mass of each substance?
For titanium, it's 48. For oxygen, it's 16.
16 grams per mole. And what do we get from here?
(1.25 moles of titanium and 2.5 moles of oxygen.
Let's see, 1.25 for titanium, you said?
1.25.
And then for oxygen, what was it again?
2.5.
2.5. So we have moles of each substance. And what's the next step I can do here?
Divide by the lowest number.
So since my lowest number is 1.25, we'll divide by that. So divide by 1.25, divide by 1.25. And what number am I going to receive or get at the end here?
1 for titanium, 2 for oxygen.
So now that I have a whole number at the very end of doing all of this, we see that we have 1 titanium and 2 oxygens. So
and that's empirical.
Exactly. So right there, let me make that red real quick. So our empirical formula would just be TiO2. Exactly like that. Is anyone confused, or does anyone have any questions regarding percent composition right now with what we just did?
I'm sorry, why you did divide by 1.25?
Because once we get the moles of all of our atoms within the composition, then we would divide all moles by the smallest number of moles. Since our smallest number of moles was 1.25, we divide all of these numbers we have by 1.25. In this case, we just have 2 here.
1.25 is also the limiting reagent.
Not really. This is not a limiting reagent. Just asking for the formula of a compound. There's no reaction going on.
Yeah, just
Yeah, I thought it was 204 also, but this says TL on the periodic table. TI is over on the column 4.
Is it now?
Yes.
Yeah, there's something over on column 13 that says TL 204.
TL204.
Yeah, be careful, guys. Remember the capitalization of the letters matters when you have your symbols. So capital C is not the same thing as lowercase c, so be careful with that.
Yeah, exactly. I know it can kind of be hard to see. You see like the dots away from the eye.
Okay, thank you.
Perfect. All right. So move on to number 6 real quick. So here we have when it's a bit wordy, but you guys can do this. So when copper oxide reacts with hydrogen gas at high temperatures, copper metal and water vapor are produced. Suppose that you start with 10 grams of copper oxide after the reaction, 7.99 grams of copper is produced. And then use the data to determine the percent composition by mass of copper oxide and the percent composition of copper oxide. Wait, is it just repeating itself? Yeah, it is. So use the percent composition of copper oxide to determine the empirical formula of copper oxide. So what's the first thing you guys think, or what's something you guys would do? You see this, what's the first thing you would write down in order to help you solve this? Any ideas or any guesses?
I forgot what it's called, but it's like that cross, you know?
The dimensional analysis table, this?
Yes.
So you want to start with dimensional analysis. All right, so let's see. Let's see, sorry, I just need to check.
I got the chat, Ellen.
Let's see. So not quite, we're not using dimensional analysis because we're not really converting yet. So what you can do here is let's see what we have here. We start off with 10 grams of copper oxide. So we have 10 grams of copper oxide, but it's not specifying, copper 2 or copper 3. That's what we're trying to figure out from the empirical. But we know from the reaction that it produced 7.99 grams of copper. And it's telling us to find the composition of mass of the copper oxide and use that to find the empirical formula. So if that's the case, we can do this. So remember that in a reaction, it's balanced. So your reactants, or your mass of your reactants has to equal the mass of your products. So if we see that 7.99 grams of copper is made from this 10 grams of copper oxide, what do you think we can do here? We can take a percentage out of this. Any ideas?
Wouldn't you divide the mass of copper by the mass of copper oxide and then multiply it by 100 to get the percent of copper?
Exactly, you would do that, yes, exactly. Since the same amount of copper from our products that have to equal our reactants, let's do that. So we can see exactly how much copper is made from this 10 grams of copper oxide. So if I divide 7.99 by 10 and then multiply it all by 100, what percentage does that give me?
(79.9%).
So we see that within this copper oxide, it's made out of 79.9% copper. So if that's the case, if copper makes up 79.9% of copper oxide, how can we get the percentage of oxygen?
Subtract that by 100 from 100.
Exactly. And what does that give me?
20.1.
We get 20.1% of oxygen now. So now that we have our percentages, now what we can do now is use our percentages like it's saying to look for the empirical formula. So like what we did with percent composition in the last problem, number 5, what can I do here to convert my percentages to an empirical formula?
You convert percentage to grams.
So let's convert our percentage to grams. And what's next? What can I do next?
You divide by the mass.
What mass specifically?
Molar mass?
The molar mass. So, well, what is the molar mass of copper?
$63.54.
63.54. Oh, sorry, I remember. Sorry about that, Sophia. Yeah, that's oxygen. So 63.54 grams per mole of copper. And what about for oxygen? What's the molar mass of oxygen?
16.
Well, yeah, 16. I was thinking of the oxygen molecule, but yeah, 16 grams per mole. So now that I divide by that, what numbers or what value do I get now from that?
So real quick, where'd the 16 come from?
The 16 came from, that's the molar mass of an oxygen atom, which is 16 grams
Yes.
per mole.
Okay.
The copper one will be 1.26.
And who can tell me what's oxygen?
1.256.
1.256 or one, or you can safely round that up to 1.26 moles. So what's the last step I need to do here?
You divide by the smallest mole.
In this case, which is my smallest mole?
They're the same.
Since they're the same, we just divide it by the same number, right? So when we divide them by the same number, we end up with 1. So we see that there's 1 copper and then there's 1 oxygen. So we put that in a formula. This would be our empirical formula. Now, real quick, who can tell me what's the name of this compound?
Copper
now?
oxide.
Can you repeat that?
Copper oxide.
You're close, but remember, the problem says copper oxide, but which copper specifically is this? Because remember, it's a transition metal.
Copper 2 oxide.
Exactly, copper 2 oxide. Because remember, since oxygen is -2, and we see that there's no subscripts to balance it out, that means our copper must be +2 to perfectly balance it out. So that.
Question.
Go ahead.
At the beginning, why do we divide by 10 grams?
Because we see here that in the reaction, from 10 grams of copper oxide, we make 7.99 grams of copper. And remember that the conservation of mass, where you must have the same amount of mass that you began and ended with. So if that's the case, we see that since the copper got removed from this oxide in the reaction, that means that we see there's 7.99 grams of copper within the whole reaction out of this 10 grams. So in order to get the percentage of that, we divide 7.9 by 10 and multiply by 100 to get this percentage. So there's 79.9% of copper within copper oxide. And with that number, we can determine the percentage of oxygen. So we subtract 7.99 by 100, and we get the percentage of oxygen, which is 20.1. So now that we have the percentages of both of our elements within our compound, we can then find the empirical formula for it.
Thank you so much.
You're welcome. Let's see, any other questions before we move forward? Nope. Oh,
so real quick, where does the 2 come from when you're talking about copper oxide 2?
So copper 2, what it is, it's whenever you're stating a transition metal in a compound, you state its charge in Roman numerals. So in this case, since our oxygen is -2 in our empirical formula, and there's no coefficients here to balance it out, meaning there's no extra copper or no extra oxygen to balance out the charges, meaning that it's 1 to 1. So we need one positive 2 to balance out this -2. And if that's the case, this copper must be +2. And
Okay.
that's what.
And that's the same thing for like iron 2 and iron 3 and stuff.
Exactly.
Cool.
Same thing applies to all the transition metals. So moving on to number 7 real quick here. So it's telling us, suppose you have a pure compound and you wish to determine its empirical formula. You find that the compound, which is a liquid, is flammable, and when it burns the sole products of the combustion, you get carbon dioxide and water. What does this tell you about the composition of the compound?
It's frozen.
Yeah.
Oh
Okay.
Oh wait.
I was like, did I
Hello?
freeze or did he freeze?
Oh my god.
That was so funny.
Oh my god. So I read that a long problem for nothing. All right, great. The recording is
You
gonna
only
be
cut
great.
out for like a few seconds, don't worry.
All right, perfect. So on to number 7. Sorry about that. So it's saying that we have a compound, and it's asking us to determine its empirical formula. But we find that the compound is a liquid, it's flammable, and it burns, where the only products are carbon dioxide and water. And what does this result tell you about the composition of the element?
Must have been a combustion reaction.
Yeah, it tells us it's a combustion, right? Where our only products are CO2 and H2O. So what does this tell you about the reactant or the main reactant that happens? What is it made out of?
Mostly carbon and hydrogen.
Yeah, mostly carbon, hydrogen, and you guys probably don't notice it, but also sometimes oxygen, because oxygen is very flammable. So exactly, so your only answer here is, since you know it's a combustion reaction and you have carbon dioxide and water, then it's really made up of carbon atoms, hydrogen, and maybe oxygen. So right there will be your final answer. This is more of those conceptual questions that you might get, but you guys got this, don't worry. So go on to the rest of number 7 here, where you decide to use the Liebig method. I don't know, I don't speak German, to analyze the compound. And you find that 10 grams of the compound produces 14.2 grams of CO2 and 8.71 grams of water, where carbon dioxide is 27.3% carbon and water is 11.1% hydrogen. And it's asking for the percent composition of the compound by mass. So let's start off by doing this. Let's write out the reaction that, let's see here, that we get. So let's start off with our products, and that's really all we have here, where we have 14.2 grams of CO2. Oh, let me rewrite that, sorry. We have 14.2 grams of CO2. And we have 8.71 grams of water. And they tell us the percentages of each compound here, where we have 27% carbon for our carbon dioxide, and we have 11.1% of hydrogen. So if our reactant is mostly made up of carbons and hydrogens, what do I need to do here in order to get the percentages out of these masses? Or actually, yeah, basically, yeah. What do you guys think I need to do here? Let's see.
Do you want some help, Alan?
No, like I get this. I'm just waiting. I asked a question.
Okay.
I asked what do you guys think we should do, and I'm waiting for, I don't know, someone to respond. So any ideas? Think about the last problem we just did with the copper and copper oxide, right? Where you must begin with what you ended. Let's see. Okay, so let's quickly do this here. If you're kind of confused, it's okay. So we see that we have 14.2 grams of carbon dioxide, and carbon dioxide is 27.3% carbon. So we can get the amount of carbon we have. So what is 27.3% of 14.2 grams?
$3.87.
So 3.87, and then grams of carbon. So we know we have 3.87 grams of carbon within our whole reaction, because remember the conservation of mass. So if that's the case, let's look over at our hydrogen here, where it tells us that 11.1% of water is hydrogen. So what is 11.1% of 8.71?
.97.
So we have 0.97 grams of hydrogen, right? So if that's the case, that means that our reactant or our compound that we're trying to find, let's see, what is the percent composition of this compound by mass? So now that we have this, we just need to add this. We need to add this up, first of all, in order to get the total mass. Because in order to get the percent composition of that compound, we need to find the total to divide it by. So what is 3.87 plus 0.97?
.84.
So we get 4.84. So let me clear this up real quick. Actually, let me rewrite that. Oops, sorry about that. Let me rewrite that over on the side where we have, oh my God, this pen. 3.87 grams of carbon and then 0.97 grams of H. And since we know that the total of our compound, is going to be 4.84 grams. And we need to find how much carbon is in this compound. So we have, let's see here. So we have CH somewhere around there. So a percentage of this is carbon and a percentage of it is hydrogen. Luckily, we have the exact amounts right here that we just got. So what percentage is 3.87 grams of carbon out of 4.84 grams of this whole compound?
Alan?
Yes? Wait,
just so you know, no, you're good, I think, but you're overcomplicating it, just so you know.
Am I okay? You want to take over, Jeremiah? I'm sorry.
Sure. So basically, I guess a simpler way of looking at it. So the 3.87 grams of carbon and the 0.97 grams of hydrogen we got, you can plug that directly into the 10 grams of the carbon that's being produced. So based off of that, wait, let me make sure I can annotate real quick. Boom. All right. So we have 3.87 grams of carbon. And in order to find the percent composition, what is it that we would need to do?
We would divide by the molar mass of carbon.
Not specifically the molar mass, but you're on the right track with mass. So which mass would we use in this case?
The 10 grams.
The 10 grams, right? Because that's what we're using in order to figure out this compound. So we divide by the 10 grams of the compound, multiply by 100. So that will give you what percent composition for carbon?
38.
Okay, there you go. 38.7% carbon. And then we would do the same thing with hydrogen. So 0.97 grams of hydrogen over 10 grams times 100. So what will be our percent composition of hydrogen?
9.7%.
9.7. Okay, so we have the carbon, we have the hydrogen. But from what we said earlier, the elemental compositions should have carbon, hydrogen, and oxygen. Well, we don't know how much percent composition we get from each of these oxygens since there's two different compounds. So the easiest way that we can do this is since there's only 3 different elements in this 10 grams, we can just, what can we do with this 10 grams to figure out how many grams of oxygen we have?
Convert it to moles.
Not quite. So we
Can
have
subtract.
carbon. Yeah, okay, we'll subtract. What would we subtract?
The carbon and the hydrogen.
The carbon and the hydrogen, right? Because basically whatever is left over will have to be oxygen then, right? So plus 0.97 or the 4.84 down there. And then you'll just divide that by the 10 grams. So what's 10 minus 4.84?
5.16.
Okay. So we have 5.16 divided by 10 times 100.
It's 51.6.
51.6% oxygen. Now, if we were to add these all up, will that equal 100%?
No. Or well, yeah.
Yeah, right. Well,
Yeah.
that's the goal. Like it should be able to add.
Yeah,
up
I was looking at 2 odd numbers and an even, and I was like, hold on. But yeah,
Yeah. Okay. So we figured out the percent composition. Is that the only thing that this question is asking for, or is there anything else?
it wants the compound of the mass.
Okay, so we got that, and then this last thing down here, it says the empirical formula, right? So how would we figure out what the empirical formula is based off of these percentages? I think someone said that earlier.
Now you do
CHO.
now you do divided by like each percent you divide it by the molar mass.
Okay, so
And
for carbon, what would it be?
12.01.
Okay. And then for hydrogen, I just like to do each one individually.
1.01.
Okay.
And then
then,
for
yeah,
oxygen 16.
16. Okay, so how many, how much do we have for carbon?
%38.7%.
Oh, I mean, like how many
Oh,
moles?
I got you.
Yeah.
Uh, 3.22.
All right. So 3.22 for carbon, and then for hydrogen?
9.60.
9.60. And then for oxygen?
3.23.
3.23. Okay, so what would be the next thing to do in order to find the empirical formula?
So what did we just do just now?
We figured out how many moles of each of these we have. So we have basically C 3.22, H 9.60, and then O 3.23. Oh, we can't have decimals for subscripts. So how would we fix that?
We divide by the smallest one.
Okay. So what would that be?
The 3.22.
All right. So what will the subscript be for carbon?
1.
All right. And then for hydrogen?
3.
And then for oxygen?
1.
There you go.
And why do we divide it by the smallest one?
We're trying to get them as close to whole numbers as possible. So if we start by dividing by the smallest one, first off, that will help us to get at least one that has a whole number, which will in this case be 1. And then that will bring all the other ones as close to a whole number as possible. Remember, try to make it less than a 0.15 difference. So like if you have 3.14, you can just round that to 3. If you have 5.86, you can round that up to 9 and stuff, or 6, sorry, and stuff like that.
So real quick, would like C3H9O3, that'd be like the same ratio of the thing, but that would be wrong?
Yes, because it's asking
Okay.
for the empirical formula specifically.
Okay.
Remember, the empirical formula is the one with the simplest ratio. So you could technically still get the empirical formula from what you got, but you'd have to simplify.
Mm-hmm. Any other questions?
Yes, I have a question real quick.
All right.
By any chance, because as I was just going through this, how did you get 3.87 grams of like carbon and 0.97 grams of hydrogen?
All right. So right here where it says that carbon dioxide has a 27.3% of carbon. So basically that percentage, what it does, it tells us the amount of grams there are in carbon or in carbon dioxide. So you know how we use the percentage of element divided by the total amount times 100% to give us our percent ratio or percent comp?
Yes.
So basically what we did is we worked backwards from that to get the amount of grams of the specific element we were looking for. Does that make sense?
Oh, okay. Okay. Yeah, it does make sense. Thank you.
Okay. Any other questions?
All right, so if there aren't any other questions, here, let me clear this up. In the event that you haven't, kind of written it down, this will be on the YouTube channel. So let me clear that so that way there's space. Sorry about that. So let's move on to the last part of this study question here, number 5. So number 8, where a gaseous compound has a density of 1.23 grams per liter at 25 degrees Celsius and 760 torr pressure. The density of oxygen gas under the same conditions of the temperature of same conditions, temperature and pressure, is 1.31 grams per liter. It's asking us to calculate the molar mass of the compound. So the compound that's not oxygen here, that has the density of 1.23. So let's see here. Let's see. So we're dealing with gases here, so like the gas law. So who has an idea of what you expect from this, or what you can do here? Let's see. So let's look at what we have right now. So we see that we have I'm just going to write it down here at the bottom. Here we have a density for unknown, which is 1.23 grams per liter. And we have a temperature, which is at 25 degrees Celsius. We have a pressure, which is at 760 torr. And then we see here that the density of oxygen under the same conditions here that we have. So O2 density is 1.31 grams per liter. So let's see here. Finding the molar mass. So coming from this, let's start off with finding the, let's see, what's it called? Sorry, my mind's escaping me. Here, Jeremiah, can you help me out here a little bit?
Okay. Well, what seems to be the problem?
No, just like it keeps slipping my mind. So like we have the density of oxygen under these conditions, but we're trying to find the molar mass of the unknown compound.
Okay. So do we have a volume? Or are we able to find the volume?
Doesn't seem like it unless you can convert your 1.31 your density.
Okay. Actually, before I say that, so we have grams per liter, right? in the ideal gas law equation, do we use grams or liters?
Liters.
We use the liters, right? So, but we don't use grams. So how can we get rid of those grams? Just ignore the liters for now. Focus on the grams. What can we do with that?
Grams per liter.
No. Like, we're just looking at the grams. Like, how can we get rid of the grams?
By grams?
Okay, so what would we do?
You need to convert it into moles.
All right, so where are we going to divide or multiply by the molar mass?
Multiply.
So we have
Divide.
grams on divide, right? Because we're trying to get rid of the grams that are on the top to put moles on top, right? So when we do that, what do we get?
So, oh,
Make sure
32,
to
thank
divide by
you.
32, please.
Oh, my bad. Yeah, I was looking at Adam. Sorry. Yeah, so this right here, let me clear up that there. This right there is a 32 because it's oxygen molecules.
Mhm.
So with our grams cancel out and we divide 1.31 by 32, what does that give us?
0.038.
So 0.038 or 0.04. Let's round it up to 0.04. So 0.04, and we follow our units. This is moles, and we see that the liters are still at the bottom, so it's going to be moles per liter. So
Yes.
now that we've converted our density from of our oxygen from grams per liter to, see, 0.04 moles per liter. So now here we have moles per liter instead of, on the grams. So let's see here.
So basically, what there's one more thing that we need to do now. So that's the amount of moles there are per liter, right? So with that in mind, how would we figure out how many liters we have? That way we can get rid of the liters on the bottom.
Divide by 1 liter.
Divide by 1 liter?
Multiply.
Multiply, right? So that gives us the conditions for oxygen gas. Right?
Yeah, this is a weird problem. Sorry about this, guys. But like, yeah, so basically what we want to try to do is to isolate the moles, and in order here to use PV equals nRT. So a good way to kind of look at this is to, since it's 0.04 moles per liter, is to let's just assume that the container we're in is 1 liter. So if we're going to be doing something like that, what we can do is, if we're, says everything seems to be pretty standardized. We have 25 degrees Celsius, 760 torr. What we can do here, if we're going to follow this into moles, is if we're assuming volume is 1 liter and there's 0.4 moles per 1 liter, we seem to have already all the conditions for PV and RT for oxygen. So if we follow the same for our unknown, we can try and find the number of moles within that 1 liter compound if its density is 1.23 grams. So let's start by doing that. So let me clear this up real quick. So let's see, so if remember PV equals nRT, what units do we need each value to be there? Like, what unit does our pressure need to be in?
atmosphere?
Sorry. Wait. First of all, Jeremiah, what'd you say?
Just real quick. So basically, since they have the same pressure, the same temperature, and based off of the density, they have the same volume. After you found the moles, you could have just went to get the molecular mass based off of that.
Oh, was it? Okay. Sorry to confuse. So we had, yeah, sorry about that, guys. So we have 0.04 moles. So continue, Jeremiah, with what you were thinking there. Sorry.
So after you found the moles, what you can do, like how we changed it from grams per liter to moles per liter, we can do the same thing with this moles and convert it to grams per liter. Because it's 0.04 moles per liter, like that was the last thing that we had. And then you would multiply by the reciprocal, or like the 0.04, you'll divide that by 1.23. Or sorry, the other way around, you'll do the 1.23 and divide by 0.04. So like, so the 1.23 grams per liter, that's given. What we're gonna do is from this ratio that we got from the PV equals nRT, the 0.4 moles per liter, we're going to get rid of the liters on the bottom. That way we just have the molar mass. We'll divide it so that it will be 0.04 moles on the bottom over 1 liter. So the liters will cancel out, and then you'll have grams per mole, which will be the molecular mass. Does that make sense to everybody?
One more time, please.
Okay, so the density that we have initially, that's basically our given. And so we know that 1.23 grams per liters is basically the grams that we have for that compound. So in order to find the molecular mass, we know that its units need to be grams per mole. And so after we found out the moles per liter that we got from the O2, we're going to use that 1.23 grams per liter and multiply it, or sorry, divide by the 0.04 moles per liter.
Oh, okay, thank you.
So that will get rid of the liters. That way it's just grams per mole, the units. So with 1.23 divided by 0.04, what do you get for your molecular mass?
$30.75.
30.75. Anybody get anything different? Everybody good? Are on the same page? So for that, okay, so since they have the same temperature and pressure, that means that if you're, okay, so basically what we have is we have P1 V1 over N1 R1 T1, which is this gaseous compound, equals P2 V2 over N2 R2 T2. So since the pressures are the same, we can get rid of those. The temperatures are the same, so we can get rid of that. And the constants are going to be the same since we use the same constants for each one. All that's left now is the moles and the volume. But since we know that the volumes are going to be the same because of the density that we used, those can also be canceled out. Well, they end up being canceled out when converting to the moles of N2, which was the oxygen gas. I don't know if that answers your question though. Any other questions? Just keep in mind, this is the first part for A. That's not the molecular formula or valence structure too. So Alan, you can take it away now.
I just realized I was muted. Here, let me clear this annotation here. Let's see, clear all. So let me move around real quick. Perfect. So right here, since now that we've gotten the, say, so here's, if we suppose that the empirical formula's compound is CH3, what would be its molecular formula? So what was the for the mass or the number of moles that we got from here, first of all? From before?
30.75.
So 30, oh, wrong pen. 30.75 moles, right? So, and in here, so this is what we calculated from this gas.
It should be 30.75.
Okay.
Just, yeah.
All right, my bad. So 30.75. And so down here, we're supposed the empirical formula of the compound is CH3. And it's asking what is the molecular. So we have a empirical. So what does this mean when we have an empirical formula versus a molecular?
Empirical is the simplified version.
Exactly. So if an empirical is a simplified version, what's like what's the simplest whole number that I can multiply this by in order to, you know, make it into a molecular formula where I can evenly distribute numbers to these coefficients and then divide them by that same number, the simplest one, or I should say the lowest one. Because remember, since the empirical is your simplified version, your empirical is a multiple of a whole number that is a multiple of a whole number that you would multiply to your coefficients from your empirical formula. So what's the smallest number I can multiply into my subscripts in order to get a molecular formula?
2.
2, right? So if I were to, let's see here in the chat, yeah, times 2. So if I were to multiply this empirical formula by 2, I'll end up with C2H6. And for this one, I know he didn't specify to write the simplest one, but that's what it is, the answer for this one, the simplest molecular formula. So we have C2H6 as our molecular formula. And lastly, it's asking us for the valence structure of this compound. So how can I draw that valence structure?
You can have like the 2 C's in the middle and then the and then you have like a bond between that.
So we have a bond. Oh, go ahead.
And then for each carbon, there should be like 3 hydrogens attached to it, like one on the top, on the side, and the bottom.
So let's do that. We attach each one on each side where they can. And yeah, this is perfectly its valence structure, seeing as carbon right now can only have 4 bonds right now. It's bonded to a hydrogen and then another carbon. And same thing for the second carbon we have here, matching the molecular formula we have here. So this is exactly the valence structure for this compound, which is ethane. Perfect. So that's it for number 5, the 5th study question he sent out. So right now, for the sake of time, because there is like a bunch more, but what I kind of want to do is ask you guys, what problems are you guys more confused about, or feel you're more struggling with, or feel you need more help with in terms of, you know, if you're coming up in your exam. So your limiting reagents, your solubility, so your aqueous solutions, redox, and gas laws.
If you feel better
say-
oriented with math.
Oh, no. No, go ahead.
No, this is for you. What's up?
Sorry. I was gonna say like half reduction and oxidation problems.
Let's see. So Sophia, can you take over for this?
Yeah. Do you have a question in mind, or should I pull some up? I don't know. I don't know what the strategy should be.
Do you not have the study questions for it?
Oh, I don't know which one it is.
Oxidation, the loss of electrons at reduction.
Question said 6.
Is it gaining?
I'm sorry, can you
Yes.
repeat that? Yeah? Oh, okay.
Yeah, so oxidation is the
answer
loss
is
of
yes.
electrons. Reduction is the gain of electrons. Because reduction, I know like it's not, it's weird how you say gain. So Sophia, well, you can set up, it's number 6, I believe.
Yeah.
Remember that when we say reduction, you're reducing the charge of the atom. So when your charge is reduced, that means the atom got reduced.
Yeah, just like as a little thing that I always think of, so like when you're reducing something, kind of like what Alan was saying, like the oxidation number is being reduced. Or sorry, but yeah, like the number, it's like becoming more and more negative. So like you can have a negative oxidation number, but if it becomes more negative, that means that it's being reduced more because it's becoming more negative. Take it away, Sophia.
So this is what I like to tell my students to remember oxidation. So oxidation is loss of electrons, right? Which means you're losing negative charge, right? Which means you're getting more positive. And then reduction is gain of electrons, which means you're gaining negative charge, which means you're becoming less positive. And then that has to do with like in the number scale, right? So this is 0. Let's say this is, I don't know, +4, right? And this is -4. If you go from -4 to +3, you're getting technically, quote unquote, more negative, right? So then, or less positive. So then you're being reduced. Does that make sense?
Oh, I think I heard something about some to learn numeracy about I think it's called oil and oil rig.
Yeah, oil rig. So oxidation is loss, reduction is gain. That's just to remember one or the other. And then another thing to keep in mind for these problems especially, there's only ever going to be 2 elements that change in oxidation numbers. So right off the bat, you're only going to have 2 answer choices for oxidation and reduction. And then you only have to figure out one of them, because if you know which one's being oxidized, the other one is going to be doing the opposite. Always, because they work in pairs.
Can you give an example?
Yeah, so let's go into the study questions if I can find them again. Sorry, I have all of the tabs open. Where is it? Study question 6, here we are. Okay.
I think there's more examples of the oxidation and the reduction half reactions in the 7 set of study questions.
Oh, sure, we can look at those instead. Study question 7. Okay. Okay. Whoa, fun. Not my computer acting up on me. I'm guessing this one is the one that you need? Yes, no, maybe?
Yeah.
Yeah, okay. So, it says the reaction you observed in lecture was aqueous copper to sulfate, so copper SO4, right? And iron metal to produce copper metal and aqueous iron to sulfate, right? So, oops, I took away half of the practice. I'm sorry, I didn't finish reading the question. So, what is the first thing that we should do for chemistry problems from here on out until you die and or you stop taking chemistry classes?
Balance?
Balance the equation, right? So is this equation balanced?
Yes.
Yes.
Yay, we got lucky. I'm so sorry I took away that practice from you guys. I didn't finish reading the question. Okay. Anyway, so then it's balanced, great. So then now what is the next thing that we should do for redox problems? So we have our balanced equation. What do we need to determine next?
Which one is being reduced and oxidized?
Okay, how do we do that?
Oxidation numbers?
oxidation numbers, right? So let's start with the easy ones. Or yeah, let's start with the easy ones. Somebody tell me the oxidation number for these two.
0.
0, right? Why is that?
Their elemental form is
Their
always 0.
elemental form. Yeah, exactly. Their elemental form, or they're by themselves. So we have an oxidation number of 0. Okay, so now what about the oxidation? Let's do the oxidation number for sulfate. Anybody? What is the usual charge of sulfate?
-2.
-3.
-2. Oh, I have a -3. Anybody want to break the tie?
-2.
-2, right? That's coming from the rule of sevens from module 2, in case you're lost. So what is the oxidation number if the charge is -2? Trick question.
-2.
Yes, -2. Because according to your rule of oxidation numbers, the oxidation number of ions is going to be equal to the charge, right? So then if this whole copper sulfate molecule has an overall charge or oxidation of 0, what does the oxidation of this copper need to be?
+2.
+2, right? Okay, cool. So then now let's do this one. What is the oxidation number for sulfate here?
Wouldn't it also be -2?
Yeah, it's also -2 because, I mean, we didn't do anything to it, right? It stayed the same. What about the oxidation number for this iron?
+2.
+2, right? And then remember I said just right now that there's always going to be just 2 elements that get changed in oxidation number. So what are those 2 elements in this equation that are changing in oxidation number?
Iron.
Okay, and what else?
Copper.
Copper, right? So iron is going from 0 to iron 2 plus, right? And copper is going from copper 2 plus to copper 0. So which one is being oxidized and which one is being reduced?
So iron became more positive, so it's being oxidized.
Okay. So then by definition, right, copper is being reduced, right? Yeah, exactly. Does that make sense to everybody?
Yes.
Yes.
Cool. Okay, now, oxidizing
I think I
agent.
do have a question.
Yeah, what's up?
How do we figure out the charge for sulfate?
So we got that from the rule of 7. Do you guys remember the rule of 7 on the periodic table from module 2? Can you see my periodic table? Can you see how, where's my finger? How sulfate is in the little square inside of the rule of 7? So then, yeah, the sulfur and the selenium have always a charge of -2 in polyatomic ions, and the phosphorus and the arsenic always has a -3 charge. Does everybody remember that from the rule of 7? It looks kind of like this on the periodic table. And then there's 4 elements in the middle. And then this one and these all have a -1 charge. And then this one has a -2. This one has a -3. And then both of these have a -3. And this one has a -2. Do you guys remember that?
Yes.
Yes.
Okay, so sulfur is this box right here. So it's always going to have a -2 charge. And that's what sulfate is always going to have, or all the sulfur polyatomic ions, we're working with sulfate, right? So this one is going to have a -2 charge. Did that answer your question?
Yes.
Okay, cool. So that's where that came from. So then now we know what's being oxidized and we know what's being reduced. So how do we identify the oxidizing agent and the reducing agent? Does anybody remember?
Oxidation is losing electrons, reduction is gaining electrons.
Okay, that's what we figured out here, right? That's what's being oxidized and what's being reduced. But what about the oxidizing agent or the reducing agent?
The
anybody
agents
remember?
are flipped of what they're actually being happening. So like if iron gets oxidized, it's the reducing agent, something like that.
Yeah, exactly. So the agents are going to be opposite of what's going on. So if iron is being oxidized, that means that this is the reducing agent. And since copper is being reduced, that means it's the oxidizing agent. What does that mean? That means that the reducing agent is the one causing the reduction, and the oxidizing agent is the one causing the oxidation. Does that make sense to everybody?
Yes.
Okay, cool. So then now, let's do the half reactions. I'm going to scroll down and risk losing everything. Okay. Where's the scroll bar? Here's the scroll bar. Okay. So I'm going to leave it here. So I kind of sort of did part of the work for you again here, right? Because half reactions, so in half reactions, we're only going to include whatever's being oxidized in one and whatever's being reduced in the other, which I kind of already did here. But there's something else that we need to include. Does anybody know what it is?
The electrons.
The electrons?
The electrons, right? So then let's do the oxidized half reaction first, because that's what it asks us first. How are we going to add the electrons into here?
You bring everything down and then it's plus, and then it should be, oh wait, I don't know anymore, never mind.
You said bring everything down, I can do that.
You would put the electrons, it'll be plus E, like on the product side?
Okay, plus 2 electrons here on the product side. Why? Why don't we have them over here?
Because when you do it on the product side, it equals to 0.
Yeah, so you're trying to balance out the oxidation here, right? So the overall oxidation on the reactant side is 0. And before the electrons, the overall oxidation on the product side is 2 plus, right? So we want to add negative charges or electrons, right? To balance out for them to equal each other, okay? It's important to remember they don't have to equal 0. They can, but they don't have to equal 0. They just need to equal each other. So like, I don't remember who said it. We're adding 2 electrons on this side so that we can have plus 2 electrons, right? 2 negative charges so that the overall charge on the product side becomes 0. So then we have oxidation that equals the same on both sides. Yes? Any questions? We're good? Maybe? No?
No, no questions.
No questions? Okay, cool. So then now let's do the reduction half reaction. What do we need to do for that one?
So for that one, it would be, the electrons would be on the reactant side.
Okay, so we would do copper 2 plus 2 electrons yields copper 0. Yes?
Yes.
Okay, and then same reasoning, right? We want to make sure that the charge equals the same on both sides. One last thing that we need to do when we're writing our pair of half reactions is we need to make sure that everything's balanced. So we have the same elements on both sides in the same amounts, right? We want to make sure that the charges are balanced on both sides. And then the last thing we want to check with the electrons is that we added them on opposite sides of the arrow and that we added the same number of electrons. So did we add the same number of electrons on opposite sides of the arrow?
Yes.
Okay, cool. So are these our final half reactions?
Yes.
Yeah, okay. And then, does anybody need this real quick before I clear it?
No.
Okay, I'm gonna clear it. So then now the last thing that I want us to do is write an ionic equation for the overall reaction. So does anybody remember how to write an ionic equation?
You write it with the charges?
Okay, what else?
You determine whether it's soluble or insoluble or soluble.
Okay, what else?
You separate each element?
Not each element, each
Well, the ones that
compound,
are soluble.
right? The compounds, right? If they're soluble, right? So then we were told that iron, oh, I already forgot what's on here. Let me see. We were told that, I'm gonna write it up here, but we'll do the ionic equation, okay? Just so I can see what the heck's going on. Okay, So we're told that aqueous copper sulfate, so as aqueous, does that mean it's soluble or insoluble?
Soluble.
Soluble.
It's soluble, right? Okay, so then if we have copper and then sulfate, right? So we said these are aqueous. So what are the charges here?
+2 and -2.
2 plus and 2 minus, right? Okay, and then we're also reacting with iron, which is a solid, right? And it doesn't have a charge. Yields copper metal, right? Also a solid. Plus, what should I add here?
Iron sulfate.
Iron sulfate, like that. Is that how I should add it?
Maybe not, by the way you said it.
Anybody want to help us with that out?
I believe it would be insoluble.
Is it insoluble? Because look what it says here. It says aqueous. We said aqueous meant soluble. So is it soluble or insoluble?
It's soluble because it's aqueous.
So you
It's
separate
aqueous, right?
iron and sulfate.
Okay, so then how would I write it?
Fe. And then what would it be?
Well, it's aqueous,
Positive
right?
2.
Positive 2. Okay, and then?
SO4 -2. And that one is
Aqueous, right?
Yeah, that one.
My writing's getting weird because you guys are like right there, but that's what that says. Does that make sense to everybody? Are we done?
No.
We're not done?
Oh,
What else
like,
do we need to do?
well, we're done, but like for the next problem, I mean.
Oh. Okay. But does that make sense to everybody? Yes? No?
Yes.
Questions, comments, concerns, panic, confusion? Sophia, what are you saying? Are you even speaking English right now? Okay. So let me clear this. Okay, so then this next part, what are you guys going to do? Do you want to practice oxidation numbers, or do you want to go straight into number 7, another redox equation? What is the chats?
Valeria sent you continue with number 7.
Number 7. Okay. Anybody want to second that motion?
I wanted to say oxidation, but it's okay.
Number 7. Okay, I see it.
A lot of people are
Okay,
saying
how
7,
about we
so.
do, yeah. How about we do the oxidations for this one, and then we do number 7. Does that seem fair for everyone?
Yes.
Okay, cool. So, what is the oxidation numbers here for PO4 3 minus? For oxygen and for phosphorus? Which of these two is on your table of rules on page 150?
Oxygen is -2.
-2, right? Okay, and then how do we find the oxidation number for phosphorus? What is the overall oxidation for this ion?
-3.
-3, right? And then we said oxygen is -2, but how many oxygens do we have?
4.
4, right? And then let's call phosphorus X because we don't know what it is, right? We want to solve for X. So then X plus -8 gives us -3. So what does X equal?
+5.
+5, right? So then the oxidation number on this phosphorus is?
+5.
+5, yeah. Does that make sense to everybody?
Yes.
Okay, cool. So yay, oxidation numbers. If you need extra practice, there's still time to go to office hours tomorrow, so there's that. So let's do Number 7, and this time I won't steal your practice. So does somebody want to tell me how to write the equation, even if it's not balanced? Anybody? No brave souls? Okay, well, what would be the formula or the symbol for iron 2?
Fe.
Fe, right? But then what does the Roman numeral tell us?
And charge of
2.
+2.
Okay, so then we would do +2, right? And then we're saying we're oxidating from iron 2 to iron 3. So that means that this is going to be the reactants, right? So then what is going to be our product for this part?
Iron 3.
Iron 3.
Iron 3, so how do we write that?
Iron Fe 3 plus.
Fe 3 plus, right? Okay, and then this permanganate ion, it tells us that we're going to use it to oxidize the iron. So does it go on the product side or on the reactant side?
Product side.
On the product side?
Oh.
I also heard a reactant side. Somebody want to break the tie?
Reactant.
Product.
Reactant. Yeah, it should
The
be.
reactants, right? Because we're using it to change this. So that means it has to be working with this. So then they have to be on the same side of the equation, right? So then let's call this MnO4 minus, right? And then we see that iron 2 plus and permanganate has a negative charge. So can those two bond together?
Yes.
Can a positive charge ion and a negative charge ion bond together?
Yes.
Yeah, right, because they attract each other. So then now we can do crisscross method, right? So then this compound would be iron permanganate with a 2 subscript, right? Okay, but it's an acidic solution. Pure leader says ayuda. I don't remember where to go from here.
So manganate would have a charge of negative +4.
Permanganate?
Yes.
No. I don't think so. I'm pretty
Has
sure on the
8. Does have 4 oxygen, which has a charge of negative 8 together.
You mean the oxidation number on manganate?
Yes.
Manganese, I mean, because that's not manganate, that's manganese.
Manganese.
Well, it has to have, so it's -2
Since
times
it's an
4,
acid,
right? That's negative
don't we
8.
get a salt in the water?
Yes.
Yes, we do. Except this is, okay, hold on.
Because if it's
Okay,
acid, you
this-
gotta add an H, and maybe you can turn that into H2O or something. I don't know.
Give me a second. One.
Yes, I agree with you. Because we have the O4, and then on the other side, we will have water, and we will make 4 H2O to have 4 oxygens and then 8 hydrogens. And then we will add the 8 hydrogens to the reactant side.
Wow. You want to explain that one?
I don't mind.
Go for it. Do you know how to draw on the whiteboard?
No, but I could explain it, and maybe you could help me writing.
Okay, but let me
Okay.
find the screen that I was on because I don't remember what screen I was on. Okay, here's the screen that I was on. Okay, walk me through it.
Okay, so the first equation that we need is the one for the oxidation half reaction. So that
Okay.
will be iron 2, which turns into iron 3. And then we have the 3 plus, and then on the other side, we have the 2 plus. So we want to balance the charges. So we would add 1 electron.
Okay.
And then for the reduction half equation, we would have, what do I have? Or for the valence equation. Which one would you like me to?
Oh, we can do the half reactions. That's fine. I mean, it's what it's
Okay.
asking for anyway, right?
Okay, well, the other thing that I wrote is that we have, I think that I'm right, the permanganate ion.
Okay.
And then it will give us the manganese plus 2. And then what Alexander explained on the lectures was that we have the O4 on the reactant side. So we would want to add water on the product side, H2O. And then because we have 4 oxygens on the reactant side, we want 4 oxygens on the products. So it will be a 4 in the water. And then because we have 8 hydrogens on the product side, we want 8 hydrogens on the reactant side. And then he also told us to look at the charges. So we have 8, positive 8 in the hydrogen. And then for the permanganate ion, we have -1. And then in the product side, we have manganese with a +1. And then for water, we would have 0, as H is 1, and then O is minus, well, oxygen is -2. So -2 times 4 will be -8. And then we have 2 hydrogens times 4.
Wait,
it will
so
be.
now, where did you add the electrons?
Okay, sorry. Okay, yeah. For the manganese, we have a +2 charge. And then we want to look at the water molecule.
Okay.
And then for O, we have a -2 charge, right?
Oh, for the oxidation?
Yes.
Here? Okay, yeah. So
Yeah.
this would be -2 and this would be +1, but they cancel out,
Yes.
so it's an overall of 0. So
Yes.
then the overall charge on this side is +2. Yes?
Exactly. So we want to
Okay.
balance the equation. So we should add 5 electrons on the reactant side. And yep.
Okay. Yes. And then remember we said last part of this is that you need to have transferred the same amount of electrons. So now the last thing that you need to do is just find a common multiplier for both of these so that you have the same number of electrons on both sides. So this one's easy because you can leave it as 5 and then we multiply this by 5. Right, Jerry? Yeah. And then you just distribute this out into the equation. So then you end up with 5 Fe2 plus yields 5 Fe3 plus 5 electrons. And then now this would be your final half reactions. Right?
Can I say something?
Yeah, go for it.
So this works, but like, I'm sorry to say this, but like, this is like overly complicating like what you could have just done instead. If you don't mind me like putting my 2 cents in real quick.
You should put in 2 cents and
Because
give
I
us the
asked for
simplest
help and you
form.
didn't come in.
It's because I heard people talking, so I waited. So, okay. So basically there are 2 important things here. It already tells us what's being reduced and what's being oxidized, right? So the first part, like, wait, let me make sure I can annotate. So the first part that's being oxidized, which is going to be your first one, the Fe2 plus goes to make Fe3 plus an electron. That's perfectly fine. And then for the reduced, well, since we know that it's going from permanganate to manganese to ion, that means that the manganese is what's being reduced. So you don't need to put the hydrogens and oxygens. You can actually just put, can you like scroll a little bit? That way I like have a little bit more room. Oh, I didn't know you annotated too. Okay, so like for the manganese, the way that you can put it is that, well, first you figure out what the oxidation number is for manganese for permanganate. So the MnO4 minus, well, once you figure out the -2 plus X equals a -1 charge, because, well, we already know that part. So the oxidation number for manganese and permanganate is a +7. So with that in mind, you can put manganese with a +7 oxidation number plus a certain amount of electrons will give us manganese with a 2+ oxidation number, since it goes to manganese 2 ion. So this manganese 2+, well, in order for it to go from a 7+ to a 2+, that means that we need 5 electrons. So we put a 5 there. And then if you need 5 electrons for it to go, then you need to take 5 from the iron. I just think that that's a lot easier for people to understand than throwing in these like H pluses and waters. Like it's right.
Oh my God, yes.
It's
I
just
totally agree with you.
Disclaimer, those H's and the water and all that stuff is Chem 2 material.
yeah,
So we're
that's
all very
why
confused as to why Dr. Alexander included it. But you know what? Whatever works, works, right? So whichever way makes more sense to you, that's what you should stick to.
I'm sorry for not like saying something sooner, but does at least one of these make sense to you guys?
Yes, it makes perfect sense. Thank you.
Sounds great. All right, take it
glad.
away, Sophia.
Thanks for helping at the last minute, Jerry. Anyway, we're coming up to the last 22 minutes of review. So now I'm counting them. So do you guys want to stick with redox, or do you want to switch to something else? How are we feeling? Oh, let me stop sharing. Let me see faces. Well, faces. What do you guys think? Also, if you're tired of hearing my voice, we can totally switch out peer leaders.
Someone says solubility in the chat.
Solubility, okay. Do you want to just like practice what's soluble and what's insoluble, or do you want to do reactions, or just a little bit of everything?
Actually, wait. For solubility, I have a little trick, cheat, both
Fair.
that I came up with that I just want to write
that
out
safe?
to you guys real quick. As safe as a heart attack. I'm just kidding.
Oh.
It's actually not that bad. Okay, so basically, because you guys will be seeing these types of elements a lot, I'm just gonna put it like this. So I went over this with my students too, but basically for solubility, if it has a plus or a -1 charge, it's gonna be soluble. The only time that this doesn't work is for halides. Oh, don't know why it's coming out so bad. Halides with the 3 poisons, mercury, lead, and silver. And that's literally all you need to remember. If you remember that that's soluble, except for these exceptions, you're good.
Don't forget hydroxide, because hydroxide's -1.
Well, oh, thank you. Oh, forgot to actually say that. Yes. Well, I mean, normally when you see a hydroxide, it's paired with, it's still good to remember that. Yeah. I just put that. Insoluble unless Yes. No, wait, that's the wrong word. Everything with a charge is an electrolyte, but not everything with a charge is soluble. Everything with a plus or minus one charge is soluble, except for these exceptions that are down here.
Your screen is doing the thing where you can't see it, Jerry.
You can't see what I wrote?
There's a big black square in the middle of it.
Oh, that's a
It's like
chat.
we can see your Zoom controls.
Oh.
My bad. That's the chat. That's the chat. Because I like to have that open. So calcium by itself is soluble. If it's calcium ion, it's soluble. Because calcium has a +2 charge. So anything that's bonded with a plus or minus charge is soluble. Okay, I understand what Gabriel was saying now. So if it has a charge on it already, it's soluble. If it's bonded, like in a compound, then you follow these rules, basically. Does that make sense? Okay. It's because you like threw me for like a curveball right there with the charge thing. I was like, wait a second, don't these all have charges? But yeah, I know what you mean now.
I'm glad you got a curveball because I had to get my own curveball all by myself.
Is that question 8? Sure. Actually,
Brooke, do you have it open?
read my
Or
mind.
what were you gonna say,
Yeah,
Jerry?
no, I was gonna say the exact same thing. Like, hey, Brooke, you
If
wanna?
you don't have it, I can share my screen and you can do it, Brooke.
No, I have it. Alan sent them to me
but
earlier.
All right, there you go.
All right.
You're not
Let me
gonna be
pull it
here
up.
for free.
It's free practice problems. Who doesn't love those? Let me share my screen. God, I have so many windows open. Set question 8. Y'all can see that, right? Awesome. Okay. Which one do we want to do? Give me a number. I know you wanted to work on aqueous one, so maybe something up here.
Did you open the one with the correction, Brooke?
No, I don't think so, did I?
No, there's the blank one. She didn't know because if she opened up the answers, then everyone would have seen the answers.
Sophia, you're giving me a heart attack. Stop it.
It's because I can't remember if he corrected the answers or the actual
The only one was the first one, which was he had bromine instead of iodine, so don't worry about that.
You make me nervous, Sophia.
It's okay, I'm nervous too.
So these look like they're all like gaseous law questions. So do you want to do these or the aqueous solubility ones with like the molarity and all that?
Just real quick, do all the students have access to the answers? They should have been emailed to you by Dr. Alexander. I think, because maybe he just emailed it to us.
No, yes, they were emailed.
All right.
Perfect. Yeah, sulfates are pretty rare. They got a lot of exceptions to them. All right. No one has given me a problem.
You know what, Brooke? Take freedom of expression. I don't know, do you feel confident in somebody just asked for number 5.
Yeah.
Number 5? Awesome. Yay. I want participation. It's like, what is it? 7:15 at night. I'm ready for a nap. And so we're gonna get through these last 15 minutes. We're gonna be good. Awesome. So it says, suppose you have a gas in a cylinder equipped with a piston. Suppose further that the volume of the gas is, let me grab a pen. Volume of the gas is 2.5 liters. The pressure is 760 torr. The temperature is 27 degrees Celsius. What will the pressure of the gas be if the temperature is increased to 327 degrees Celsius and the volume is held constant? So we're working with gas laws. Which gas law do you think would be a good idea to use in this equation? Anyone want to tell me?
I'm not too sure, but I know that we can use like the PV over nRT equals PV over nRT. Like we can
PV
use
over
that.
nRT.
Yeah.
Yeah, that's pretty good. An easier one that I personally find, and I think that this is a pretty useful one to use throughout gas laws just in general, is this guy. P1 V1 over T1 equals P2 V2 over T2. I like this guy just because he works for a lot of problems, and even if you don't have all the stuff, you can usually cross out what you don't need. So when we're looking at this guy,
Can I cut in real quick, Brooke?
What's up?
Sorry, with what I think it was David said. So PV over nRT equals PV over nRT. You can also use it. And then what I like to do is cross out whatever is staying constant. And
Yeah,
then that way you get whatever you need. But yeah, he's not wrong.
No, you're not wrong. Trust me. There's like in gas laws, there's literally a bajillion different ways to do one problem. This just is mine. If you find something easier that works for you, that's cool. If not, it's what you like. So I like this one just because I can maybe handle about 3 variables before my head explodes. So we're gonna work with this for right now. So we have P1, V1, and T1. So our pressure one it's usually the first one they give you. So in this case, it'd be 760 torr. Our V1 would be 250, and our T1 would be 27 degrees Celsius. What's up with our T? Something's weird with it. What do we gotta do?
It's gotta be in Kelvin.
Kelvin, awesome. So how do we convert to Kelvin? Can someone do that?
Add 270.15.
Beautiful. So when we add, it would be 27 plus 273 point, God, you can't see black on the side, sorry. 27 plus 273.15, and what did you get?
300?
300?
Yeah.
Degrees Kelvin, perfect. So we know that, oh yeah, and what's another thing? We have this guy who needs to be in Kelvin. What's up with our pressure?
Needs to be atmospheres.
Atmospheres. How are we gonna get this guy to atmospheres?
Isn't 760 torr 1 atmosphere?
Perfect. Yeah, if you look at page 162 in your workbook, we have like a table of all the different measurements and how they equal an atmosphere. So we already know 176 equals 1 atmosphere. You can also set up like the fence method or everything. Similar idea, same idea. So we have our set it first. So we have pressure is 1 atm times volume 1, which is 250. We didn't have to mess with him because he's already in liters, which is less work for us. Awesome. And we found out our temperature is 300 Kelvin. Let's look at our second half. Let me switch colors. Let's hit orange, UW, School Pride. What will the pressure be? So it's asking for pressure. So this is our unknown of the gas if the temperature is increased to 327 and the volume is held constant. So one thing awesome about this, volume held constant. We don't got to do that. We don't got to mess with them. You can just pop in the equation like that. 327 Celsius, what do we have to change that to?
Kelvin.
Kelvin. So just like before, we have to add 273.15, and what do we get?
600.
600. That is like freaking hot. It's like El Paso during the summertime, how it feels. Extremely hot. So we have 600, and we have X, what we're trying to find. So we have everything. What can we do to manipulate this formula and solve for X?
Multiply both sides by 600.
Beautiful. Let's start with that. So we have multiply 600. You can't see my writing. I'm super sorry. I should have thought about that ahead of time. So these guys would cancel out. And we're left with this equation, 600 times 1 times 2.5 over 300 equals x times 2.5. What do we have to do now?
Six hundred
Divide.
times 2.5 is 1500, and you just divide that by 300.
Yeah, exactly, same idea. Another thing you can do is divide again by 2.5. And if you notice, if you divide this over here by 2.5, this would all connect, and then these guys would cancel out. So you would eventually just have the equation. Can I scroll down? I can. I'm going to work over here so you can see. You eventually end up with the equation 600 divided by 300 equals x. So what would our answer be?
That's a lot of work for 2.
Exactly. 2 what? What are we looking for?
Atmospheres.
2 atmospheres. I don't know. It doesn't tell us exactly what units they want their pressure, but let's assume because they gave us torr, he's looking for torr. I don't know if that's on the answer key, but let's say, just in case you need to know, how would you convert 2 atmospheres to torr?
Multiply 2 at 760.
Yeah, if you want to set up that fence method, it works just the same. 1 atmosphere equals 760. Blech. Torr. And what do you get as an answer?
1520.
1520. God, I can't like write correctly. That would help. Woo. So this would be your answer. Good job. Does anyone have any questions on how we found that? Yes, no, maybe?
No, thank you.
Awesome. So it's 23. We probably have time to do one more question. Do we just want to keep going on module 8? Do we want to do like one of those, like 6 or 7 or something? Yes? Okay. Oh my god, my back needs to crack. Wow. I'm gonna erase just, let's do, gosh, the controls aren't working. I'm just gonna erase this so we can work with number 6. Okay, so suppose you add air to one of your automobile tires to adjust the pressure to 30 psi on the coldest day of the year when the temperature is negative 10 degrees. What will the pressure be in the tire on the hottest day of the year when the temperature is 40 degrees? Assume the external pressure is 13 psi and your tire has no leaks. So, same idea that we're working with. What do we think we're going to need for this problem?
A gas law again?
The gas law? Yeah, we're working with gas laws. Thank God. So,
Quick question.
what's up?
You did say that the one that you like to use, like the P1 V1 over T1, you know? You said that that one works with almost everything, right? Or
Yeah, I like him because I like him just because he's good to work with when you don't have to worry about things like moles. So like in this problem over here in number 5, they didn't give us a specific gas. Like they didn't say this was nitrogen because that might be a hint that you might need to find its moles. But the same thing like we said, if you wanted to use this one, like the PV over nRT equals PV over nRT, and these are all like, this is 1, 1, 1, 1, 1, and this is all 2s. It's the exact same thing. You would just like start canceling out, like you wouldn't need your moles or your constants, and you would eventually get the same equation as you see. So if you want to memorize just one equation and then know how to manipulate it, it's the same thing. I just like this guy just off the bat. He's also known as the combination gas law in your book. So these two I like to play around with a lot, but that's just me.
Okay, thank you.
No problem. Can we also use the STP condition for number 7? Do you want to work on number 7 instead of number 6?
Oh no, it's because I thought we were working on number 7. That's why. But no, that's fine. We can work on number 6.
Yeah, sorry. I got lost looking at number 7. So we have we have a color change of pen. So we're given a pressure, a few temperatures, and another pressure. So I'm thinking we're gonna work with the similar idea. What's the first noticeable thing about this guy? What is he all about?
It's in PSI, not atmosphere.
Yeah, he's in PSI, which makes sense because usually you use PSI on tires. So I mean that's cool, but atmospheres is what we like to work with. So what is 35 PSI if you want to convert them to atmospheres? And if you look on page 162, they tell you that ratio. What numbers do I have to fill in this little thing?
It will be 1 ATM.
Oh, sorry, put that in wrong. Yeah, 1 ATM?
Yes, and then it will be 14.695.
Perfect, 14.695. So again, use self-dimensional analysis, multiply across the top, divide by a bottom. I wrote that really small, but what do you get as an answer in atmospheres?
I got 2.381.
Awesome. So 2.381 ATM. And the next thing we look at is, let me erase that circle, is our temperature. So this guy is in what?
Celsius.
Celsius, and we want to go to?
Kelvin.
Kelvin. Same routine we just did. You add 273, and what do you get?
263.
260.15. Perfect. So now we have let me change color so you can see it. Let's get a fun color. Let's get purple. So we have a pressure one and we have a temperature one. Yeah, awesome. And we're given temperature 2, but he's also in Celsius, so let's real quick convert him to Kelvin. So we have, I'm just going to move down here, 40 plus 273, and what do you get? 915.
I got 313.15.
313.15, awesome. That's yeah, I didn't write him over here, that's Kelvin. He's gonna be our T2, magenta. Ah, I broke it. I didn't break it, stop talking. Okay, so now, so just kind of like conceptually, if this is what helps me. If I know that pressure and temperature are related, that like if pressure goes down, temperature goes down, if temperature goes down, pressure goes down, they're going to be related to each other. So if I know that the temperature is going up, I should probably be thinking in my head, the pressure is probably going to go up as well, just to keep in your head. So, give me a sec. I believe you do is use this equation. Again, this one, the P and RT works as well, but this guy also works. And because we don't have any volume on either side, we can take him out. So currently, we're looking at P1 over T1 equals P2 over T2. And peer leaders, feel free to stop me if I say something wrong. And we just plug in on what we found. So we have our PSI, which we found in atmospheres of P1, which was 2.381, over T1, which was 260.15.
Shouldn't that be 263?
263, is that what it is? Yeah, okay, I wrote it wrong. Nice catch. Then let me erase it. 263, and that equals to what we don't know, our P2. So it's going to be our X over our T2, 313.15. Pardon. So now, how would you solve for X?
We manipulate the equation.
Perfect, and how we're going to do that?
We multiply by the reciprocal, so it'd be times 3.15 on both sides.
Perfect. So we multiply by 313.15. These guys will cancel, and this is your new calculation. So what do we get for X?
I got 2.83.
What did you get? Can you repeat it?
2.83.
All right, did anyone else get this? Yes? Awesome. Okay. Excuse me. So now we have this in, what is this currently? What's the units for it?
Atmospheres.
Atmospheres? Cool. And what did we originally have?
PSI.
PSI, so let's convert this back to PSI. So I'm going to move down here just to have some more room. And what do we put on top?
$14.69.
Perfect. 0.6595. I like to use all the decimals because I'm extra like that. All right, and then we do this equation. We multiply across the top, divide by the bottom. What do we get?
$41.58.
18. So that is 4118 PSI. So that would be your answer. Just remember that like the rounding and stuff, it'll probably lead you to have a different answer because remember it's all like a range. Some people might use 2 decimals, some people might use like 10,000. It's all like a range, but you should get close enough to find an answer.
So remember that as I butt in here, remember that like it's multiple choice. So if you get something like 42 and the answer's like 43 or 44, then you can probably assume that it's that you got the right answer. Because again, like Brooke said, like people use different amounts of decimals, different accuracy, so it's gonna be within that sort of range that you can round up to. But don't assume that like say you have like an answer of 41 and the answer is in like the only selection is 48. You may want to go back and check that because that's like a bit too big of a difference.
Then another thing you can do to decrease that rounding error is to be careful with your rounding. Like for example, here we rounded, and then I'm pretty sure here we rounded. So just be careful how many times you round within the problem, because that's going to give you more and more of a rounding error. But you should be close enough that it shouldn't affect you too much.
Yeah, and the whole thing like Kelvin, some people add the 0.15, some people don't. It's all based on what you have. So if sometimes you don't get the first one, try again, but with different rounding numbers.
The 0.15 on the Kelvin, do you think it'll be too much of a difference without using it?
No. It should be fine. Just in case you're like super skeptical, and you're like, I want to just double check and make sure, you can try it with or without, but you should get in the same area, and it shouldn't be that much of a difference.
For me, my rule of thumb is that when converting to Kelvin, I just add it to 273. But if it tells me that it's under STP conditions, then that's when I would use the 0.15 just in case.
Okay, thank you.
Okay, so yeah, perfect. So let me just quickly pause the recording.